Okay, so let's see how this goes. This is your bonus lesson, day 4, nuclear chemistry. Okay, and once again, this is in your homework packet, and it's also in your notes packet, and you'll have a separate test over this if you choose to take it. You will not have any on your regular test, so this is just if you want to do it. This is a bonus lesson. So here we go. So because we're talking about nuclear chemistry, nuclear means nucleus, and so we're talking about what happens inside of the nucleus of an atom, specifically to neutrons and protons. Okay? So nuclear chemistry, what we just said, the protons and neutrons make it up, and atoms with the same amount of protons but different neutrons are isotopes. And so this is going to be a small review of last unit of how isotopic notation and isotopes work. So nuclear means that the nucleus.
At this time, please use band cheer, Liberty Bells, and ROTC for that run. Thank you.
Okay, the nucleus, so what's going to be happening with the nucleus, all right? So here you can see that if something's radioactive, that means it's going to be giving off energy, and when it gives off energy, it's also going to be giving off some type of particle, okay? This is going to mean it's unstable, okay? And so nuclear chemistry is all about the unstableness of the nucleus of an atom, okay? So just a review of isotopic notation. We have subscripts, which are down here, and we have superscripts, which are up here, okay? And then we have your symbol, your element symbol, right? So this right here, to review, is your mass number. Let's see if I can do this without mass number. And this right here is your proton number, okay? Your atomic number, okay? So in this case, this is going to be called hydrogen 3. Hydrogen 3, all right? Remember, because in isotopes, we say the element name, and then we say the mass number, okay? The subscript is the atomic number. The superscript is the mass number, all right? So to find how many how many neutrons there are, protons plus neutrons equals the mass. Well, when you have isotopic notation like we have here, the math is pretty easy because it's set up. 3 is the mass minus the 1 should give you 2 neutrons, which have no charge, okay? So once again, mass minus 1 should give you the number of neutrons. So just to review once again, this is element carbon. You can write in here. The mass of this carbon is found here, so it's 12. Protons are found here, so protons was 6. And to find neutrons, we take 12 minus 6, and that will give us 6 neutrons, okay? Next one, same concept. Element goes here. Mass is found right there. Protons are found there. Neutrons are just 19 minus 9, and then that number will go there. And that's where all of those numbers came from, okay? So how would we say this? This is fluorine 19, because this is an isotopic notation, so it's understood that this is an isotope. So we say isotopes by their element name and then their mass number. So fluorine 19, okay? So same concept, copper, mass is 63, protons 69, neutrons 63 minus 29, whatever that number is, goes there. And there you go, okay? Same concept, uranium, mass is 235, uranium 235 is how you would say this. Protons from this number here, and then neutrons, when I subtract the mass from the number of protons, that number goes in that line. It's the number of neutrons, okay? So write isotopic notation from an atom with 15 protons and 16 neutrons. So once again, we have our symbol, atomic number, so this number of protons goes at the bottom. Neutrons, we don't go in there, doesn't go in there, but we do need it to give our mass number. So this is going to be 16 plus 15 should give us 31 as our mass number, our atomic number is going to be 15. Because our atomic number is 15, we look at our periodic table, and element number 15 is going to be phosphorus. So we put a P there. Okay? And that's where all those numbers came from. Okay? So once again, proton number goes at the bottom, so this would be 67. Neutron number doesn't go anywhere, but we need it, so it's going to be 95 plus 67 is going to give us that number. And then, because this number is 67, the 67th element on our periodic table is where'd you go? HO, hafnium. That goes there. And that's where all these numbers are going to come from. All right. Same concept. 31 goes there because that's our number of protons. 31 protons means we're looking at element number 31, which is gallium. Okay. And then because they give us the number of neutrons, that means I take 41, I add it to my number of protons, and that should be 72. Let's see if those numbers, and there you go. Okay, so these are some nuclear chemistry vocab words. Radioisotope, an isotope that has an unstable nucleus. So radioisotope. Radiation, the energy that is released by nuclear change. So because these things up here are unstable, they're going to give off some type of energy called radiation. All right. So what makes a nucleus unstable? Neutrons help hold the nucleus together. The nucleus only becomes unstable if there's not enough neutrons or if there are too many. So if we don't have the right amount of neutrons, or we have too many, plus or minus, that's what's going to make it unstable. A stable nucleus depends on the proportion of neutrons to its protons in the nucleus. A stable nucleus depends on the proportion of neutrons and protons, right? And so we get these charts here, all right? And so what's you see here is that your green here is going to be stable and that your red is going to be unstable. So what that means is this hydrogen right here, hydrogen 3, is the most stable form of hydrogen. Hydrogen 1 and hydrogen 2 exist, but they are extremely unstable. So anytime you see the green here for any one of these elements, this green area, and over here, that's going to be a stable form of that element. Anything in the red that I'm circling here, anything in the red squares are going to be unstable. Okay? Anything in the gray area over here is not possible. Okay? So these are all possibilities, but they're stable or unstable, and the gray is going to be not possible. Okay? So band of stability, once again, in this area, this green area, so this thin line that goes from the middle all the way up through here and stops here, that's going to be stable isotopes, and all of the orange, yellow is going to be unstable, and anything out here in the white or down here in the white is going to be non-existent. Okay, so the question is that an isotope of neon has 10 protons and 16 neutrons. Is this isotope likely to be stable or unstable? Okay, so if I have 10 protons, well, here's your number of protons, which means I'm going to start at this line. And 16 neutrons, well, here's our neutrons on the x-axis. So 16 neutrons are going to be, if this is 10, we're going to be about right here. So when I grid this up, what is that most likely going to be? Well, it's going to be, if I have to pick one of these two, a radioisotope which is unstable, or is it going to be stable? My answer is going to be this, because it does not fall within that green line, that green sliver throughout the middle of the graph. Okay? An isotope of uridium-90 likely to be which one? So this is where we have to use the isotopic notation, because I have my mass and my amount of protons. Well, protons are going to be over here, so I'm going to be just below that 40 line. And then now I need to find my number of neutrons. So on to the side, 90 minus 39 is what? That's what you need to figure out. So if you have a calculator, 51 this is going to have 51 neutrons. Why did I need to do that? Well, I need to come over here. 51 neutrons falls about right here. So when I grid this up, I fall right in the middle of that green. So this is going to be stable. Okay, an element, protactinium, has 91 protons, so I'm going to be all the way up in this area of the graph. Could stable isotopes exist? So 90 is going to fall right here. I know it's kind of hidden by I'm going to draw a line. So this is your 90 line up here. So when I draw this line all the way across, I notice that it doesn't fall within any green area. So could it exist as a stable isotope? Could it a stable isotope? Well, since it does not fall in any of the green, I need to choose that no, it's too big. It will exist as unstable, but not stable. Okay? So radioactive elements are still around 15 billion years. Why? Are still around after 15 billion years. That's because of their half-life, because some of them decay so extremely slowly. There are some isotopes that decay very, very quickly. Within minutes, they're going to be gone. Okay? So the half-life of an isotope is defined as the time it takes for 1/2 of the nuclei to decay. There are 3 ways to ask half-life questions. So here's one. How long will it take for a 120 gram decay to 7.5 grams? Okay? And then we have all of these other types that you can see. So if I have thallium-208 has a half-life of 3.053 minutes, how long will it take for 120 grams to decay to 7.5 grams? So if I start with this amount and I eventually get to this amount, right? It takes this amount of time. How long will it take? Well, how many half-lives did we go to get to 0.75? Well, if I take 120 and divide it by 2, I get to 60, right? And if I take that 60 and divide it by 2, I get to 30. And if I take 30 and divide it by 2, I get to 15, right? And if I take 15 and divide it by 2, well, now I'm at 7.5, which is where I'm supposed to end at. So because I went through this amount, here's one half-life, here's my second half-life, here's my third half-life, and here's my fourth half-life, okay? Because it's half-life, I can divide by 2, and I end here, so I went through 1, 2, 3, 4. And each one of these half-lives is this amount long, 3.5. This is actually very quick. So if I take this amount of time and multiply it by 4 half-lives, because I went through 4 half-lives, how long will that be? Well, I'll take my calculator, and 3.053 times, since I went through 4 half-lives, times 4, I get 12.212 minutes. Okay, and I can check sig figs. There are 1, 2, 3, 4, 1, 2, 3, 4. So technically, 12.21 minutes is my answer. Okay. The next type that you could do, gold 198 has a half-life of 2.75 days. So every 2.75 days, it's going to be decreased by half. Okay? How much of a 96 gram sample of this amount will be left after 8.1 days? Okay? After 8.1 days. So how many half-lives are going to be in 8.12? So if I take 8.12 and divide it by 1 half-life, so 8.1 divided by 2.7, I see that this answer is 3, which means I've gone through 3 of my half-lives. Okay?
And to the students at this time, all students who are on the Pep Rally list may be released to senior campus. You again, all students on the step early list are released to senior campus. Thank you.
So if I start with 96 grams, I need to get through 3 of my half-lives. This is not 3.5, this is just 3 half-lives, okay? So after 1 half-life, 96 divided by 2 is going to be 48. That's 1 half-life. If I do this again, here's my second half-life. 48 divided by 2 is going to be 24. Right? 48 divided by 2. And because I need to get through 3 half-lives, I need to do it one more time. 24 divided by 2. Here's my third half-life. Then I'm going to be at 24 divided by 2 is going to be 12. So I'm going to end how much of a 96 gram sample will be left after 2.7 days? 12 grams. Okay? Because in 1 half-life, there's 27. How many days did I go by? That's why I found out how many half-lives I'm going to need to. And then I take 96, go through 3 half-lives, and I get 12. Okay? The last one. So we give you the other pieces of information, and you need to figure out what the half-life is. Okay? So what is the half-life of carbon-14 if, let's see here, 100 grams, okay, decays until only 25 grams are left after 11,460 years, okay? So I know my beginning and I know my ending of 25, right? So how many half-lives did we go through to get from 100 to 25? Well, if I take 1 half-life, that gets me to 50, right? That's 1. And my second half-life will get me to that 25. So I've actually gone through 2 half-lives in this one. Well, if carbon is left after 11,460 years, what is the half-life? If I start with, if it took 11,460 years to go from 100 to 25, and it took 2 half-lives, well, if I divide this by the number of half-lives I've been through, that will give me the amount of 1 half-life. So 11,460 divided by 2. That means each half-life is 5,270. Oh, sorry, that's wrong. 5,730. Just read my calculator wrong. Okay, so I know my beginning my beginning amount. I know my ending amount. I needed to figure out how many half-lives it went through to get from beginning to end, and then if I know how much time passed, if I divide that by how many half-lives I figured out, that's how I got how much 1 half-life is. Each one is 5,730 years. Okay, so that is half-life. All right, so the next part of this is types of radiation. All right, so we have 3 types of radiation: alpha, beta, and this is gamma, right? That's gamma. That's a gamma symbol, okay? So to start with alpha decay, right? Alpha decay is your least energetic, all right? Not a lot going on, but it still is a type of decay. Alpha decay is really when we get rid of a helium atom, okay? So we start with uranium-238, and because of this alpha decay that we see here, we're going to get rid of a helium atom, isotope, with a mass of 4 and 2 protons. This is called an alpha particle, all right? And so it turns in, because we're getting rid of protons, anytime we get rid of protons, that's where that 90 comes from, we're going to change what element we're in. Okay, that's been something we've talked about. Because we're changing protons, we've changed the number of elements that we're in. Okay, so anytime you're getting rid of or you're decaying off of a helium, that means that's going to be correlated with an alpha decay. A large atom becomes more stable by ejecting an alpha particle, which is just a helium element or isotope. 2 protons and 2 neutrons to get a mass of 4. Okay. So the big part of this section is you're going to have to be able to read these nuclear equations. Okay, and they look a lot harder than what they are. So what you need to notice is that this uranium that you see here, this uranium, went from 238, and then it went from a mass of 238 to 234. But also, it went from a number of protons of 92 to 90, okay? Which means to get the right side to equal the left side, this is what has to have been emitted, okay? So the characteristics of alpha decay is that the atomic number, okay, decreases, which is here, the atomic number decreases by 2, and the atomic mass decreases by 4. Okay, so this uranium, because it went through this decay, the decay is indicated by that arrow. It goes from 238 to 234. Well, that's this part right here, the green. The mass went from, the atomic number went from 2 to 90. That's the blue. Okay, and because of that, we can say that we had alpha decay. Okay, so scientists observed radioisotope emit an alpha particle and became a stable isotope. The new isotopes, so what's going to happen? Atomic number decreases by 4, atomic number is unchanged, mass is 4 less, mass is 2 less. So if I come back here, it says that mass decreases by 4, so there you go. Mass number is 4 less. All right. Next one, beta decay. So when you have beta decay, all right, you're going to have what this symbol looks like up here, and it's going to look like this. It means a neutron has been released in a high energy electron, okay? Beta particle, and it turns into a proton, all right? So let's look at the equation. So what happens here, the big thing with the equation is your left side has to equal your right side. Okay, and so this is a neutron. Neutrons don't have any protons. This is just a particle. It's not an all-around element like alpha decay was, and it has a mass of 1 because neutrons have a mass of 1 AMU. Protons, well, there's 1 there, and there's 1 mass number because it's 1 AMU. Okay, and electrons we indicate with a -1, and electrons do not have any mass at all. All right, so if I look at this, how do I know what's going on? Well, this iodine isotope, first off, has a mass of 53, and this is iodine 131. How do I know that beta decay has happened? Well, electron, I'm looking for this electron. Because electrons don't have any mass, if I look at my mass numbers, they stay the same because electrons don't have any mass, but I'm giving off a proton, or I'm accepting a proton. An electron has turned into a proton, and so that's why that has turned into 54. Okay, it increases by 1. Okay, it increases by 1. A neutron has really turned into a proton. That's why your mass is unchanged, and we're giving off an electron over here. All right. So scientists observe an unstable nucleus emit a beta particle. Afterwards, the nucleus is going to do what? The atomic number increases by 1. Atomic number decreases by 1, mass number gains 1, or mass gains 2. If I look back here, there's no change in the mass, so these two are gone. If I go back, it says atomic number increases by 1. Atomic number increases by 1 is right there, because it's in beta, it's a neutron becoming a proton. Okay, and then in gamma radiation, this is just all electromagnetic waves. So there is no change in mass, there is no change in atomic number. This is straight energy. Now this is very high energy and very dangerous, but there's no change to the overall equation. So gamma rays are usually released along with alpha or beta radiation, and the symbol is this Y-looking symbol. Okay? So if you don't see any change overall to the beginning, to the reactant part of the side of the equation, then it's going to be gamma radiation. All right, so when I look at my radiations, this is showing how dangerous they are or how penetrating they are. So alpha, like I said before, alpha cannot even make it through a piece of paper. Okay, beta can. Beta can make it all the way through the paper, but it gets stopped by a somewhat thick block of wood. Gamma actually goes through all of that, and actually can sometimes penetrate concrete, and that's why when you take X-rays, instead of concrete, you wear a lead vest or a lead covering, because of the gamma radiation coming from X-rays can't penetrate that. Okay? So that's the penetrating power of each one of these and how dangerous they can be. Beta can be somewhat dangerous depending on how much you're exposed. Gamma is very much dangerous, especially with long exposure. Okay? So here's a foldable that we could have done in class. You can make it at home if you feel like you need to. Here are the symbols that you need to, the rest of the foldable, some notes that you can put down. Okay, once again, this is alpha. I can't really draw, I don't know if I can draw an alpha. An alpha, this is beta, and then this is your gamma, right? The betas, this is the neutron turning to a proton, and then your alpha, this is where you're going to have your helium isotope be given off. Okay, so to test yourself, order the nuclear radiation from most penetrating to least. So least powerful to from most powerful to the least powerful. So I know that gamma is the most, and it says to go from most to least. So A and B are out. So then I know that gamma, beta, alpha is the correct order there. A scientist exposed to a nuclear fuel source, after the exposure, he only exhibits symptoms of tissue burn and mild radiation. What type of radiation? So mild tissue burns is probably going to be beta. If it was severe stuff, severe radiation sickness, that would be gamma. And the next one, atoms can eject or emit neutrons to help the nucleus become stable. This is your neutron emission. Don't worry too much about this one. Okay, so we need to balance each side of the equation, so we're going to do some balancing with those equations that we talked about. So here we go. And once again, this is your reactant side, this is your product side, and no matter what we do, the left side has to equal the right side. Okay, so here we go. There are 3 steps to balance a nuclear equation. Balance the mass number on top first. So very easily, 232 has to equal 228 plus some other number. So when you put this into your calculator, it's very easy. 232 minus 228 gives you 4 as your superscript. Then the same thing on the bottom. Has to give us some, this 90 has to equal 80 plus this number here, right? So 90 minus 88 equals 2. Well, because this number is on the bottom, I know that each one of these numbers is a proton number or atomic number, so I know that the proton number for 2 is going to be helium. Well, now that I know that this is helium, I remember from my notes that anytime I have helium in my equation, I know that I'm going to have some type of alpha decay. Okay? And that's what the rest of this is going to show you, those numbers that we came up with. Right? Let's go back here. All right, so this is some type of alpha decay. You should be able to do that. Now, I could very easily take out any one of these 3 terms, and you figure out what the missing term is and what type of decay it is, and that's what we're doing on this page here. Okay, so we start with lithium 9, and if we balance the top numbers first, so 9 minus 9, well, that's going to be 0. That means our mass does not change. We should think back to our notes. Which type of decay has 0 change in the mass? And if I go from 3 to 4, well, the only thing that I can do here to get this number to be correct is a minus 1. 4 minus 1 gives me 3. Well, what particle has a minus 1 here and a 0 up top? Well, that was our electron, right? This is an electron, sorry, a neutron turning into a new proton. So this is going to be a type of beta decay. Okay. The next one, I have 140 and 62. Well, 140 has to be something plus 1, which is 139. So 139 plus 1 gives me that 140. And then I have 62. Well, this is 0. That means this has to be 62. Okay? Because this is 62, that means my element has not changed. It's just still going to be Sm. Okay? And this is your neutron emission, because this is a neutron. That means we're getting rid of a neutron. Okay? Protons stay the same, and then your mass stay the same because, or sorry, goes down by 1 because we got rid of a neutron. All right? At the bottom, I have bismuth 209, and so we need to figure out what this middle term is. Well, if I do the math, 209, this number plus 4 has to equal 209, so this has to be 205, right? And then this down here, this number here has to be 83. This number plus 2 has to be 83, so this has to be 81. Well, if I go to my periodic table, element number 81 is TL. And because this is helium, this is going to be an alpha decay. Okay? And there you go. Okay, so there's a few more examples that you can go through. I'll also do some examples on the homework video that's coming up. All right, so be looking.